A pretty good crowd at the moment. So let's go ahead and get started. Thank you all for coming to the LPI virtual seminar this week. Our guest is Dr. Jessica Sunshine, who is a professor at the University of Maryland and previously worked on the Deep Impact mission and is an expert in spectra and studying the comet. So to share her talk today, or is titled "All Comets Are Somewhat Hyperactive." So I think without too much more ado, take it away, Jessica. Thank you so much for coming.
Yeah, thanks, Sean. I really appreciate the opportunity to be here, at least virtually. So I see some familiar faces, but I mostly see familiar names. That's okay. Understood. I would just start by saying I'm used to being interrupted. I did 2.5 semesters, almost 3 on Zoom, of teaching. So please stop me, just yell out whatever, easy in the middle. I don't mind whatsoever. That would be great. What I'm going to do today is talk about a topic called hyperactive comets. And I should point out from the beginning that a lot of what I'm going to say is in a paper that was recently published in the Planetary Science Journal by myself and Lori Figi. Lori's definitely responsible for a lot of the great stuff that I'm going to be talking about, but it's not her fault for sure, whatever it is that I end up saying here. What I'm going to do is start by talking about comets in general and a little bit about their complexity as far as we know it as a class of objects. Then talk about a very small set of interesting comets that are in fact called hyperactive and why we call them that. Then get into what the implications of what we learn from these hyperactive comets are for comets in general. And at the end, get into a little bit about how this might affect our strategies for someday collecting and sampling cryogenic material from comets. So we'll go along. Okay, so when I say that we've known that comets are diverse from the beginning, I really mean it. This is, as far as I know, the oldest record we have of comets. It comes from a silk that was woven in China some 300 years before the Common Era. And it catalogs in total 29 comets that date as far back as about 1,500 years before the Common Era. And what you can see here is a really beautiful example of, I can't really tell you exactly what they were trying to catalog, but you can see just sitting back that these comets aren't all the same. Their tails are different. Somehow their total shape appears to be different. And there's a great diversity left in this really wonderful artifact we have from a long time ago. And our opinions about the diversity of comets has just gotten more complex with time. So let me first remind you that comets are very frustrating things to study. When they are close, they are highly active. That is, the sun sublimates ices on their surfaces, and they create their own coma, which is exciting, has a lot of chemistry, lots of stuff to watch, but it does in fact shield the nucleus pretty much entirely from our ability to see it when it's close enough to resolve. We do gain an awful lot of information about comets with telescopes, variations in their activity, their coma chemistry and morphology, which I'll talk about in a little bit more. But in terms of the nucleus, it's basically hidden from us when the comets are close. And when comets are far away, they largely are inactive. They're far from the sun. They are often bare nuclei, but those nuclei are very dark, 3 to 4% albedo, which for the record is darker than charcoal. So they're far away, they're small, and they're dark, which makes them almost impossible to study. So for a long time, our understanding of what a cometary nucleus looks like, the core of a comet, was left with theory. And some of that theory was really impressive, particularly for when it was put together, not the least of which came from Fred Whipple in the 1950s. First of all, there was this concept that comets are sort of leftovers in the formation of the solar system, and they're just little piles of fluffy aggregates of homogeneous material, something like this here shown on the top. And Fred had this concept that in order to have the kinds of gas emissions that we see, we might want to think of comets as dirty snowballs. And we've evolved from that idea because we realized that there's actually more dust than ice in comets in many cases. And sort of euphemistically, it's now called the snowy dirtball model. But that's what we had. And there's an implicit assumption about all of this concepts is that all comets and all parts of comets are the same, and activity is more or less uniform. Now, that certainly isn't the case, as you're going to see here today. But in terms of actually seeing the cometary nuclei themselves, we really didn't have a chance at all until we started sending spacecraft missions. And in this case, although we've learned a tremendous amount from the spacecraft missions, they're very few and far between. So one of the things that we started to realize when we put together sort of the pictures we started getting from spacecraft is that there's an incredible unexpected heterogeneity among cometary nuclei. And I should point out that there's one comet missing from here, a very important one, 67P, the target of Rosetta, but we'll get that in the next slide. But you can see these are now all on the same spatial scale, and Hartley 2 is blown up here, so you can see it. It's the smallest of these. There's really a wide range in shapes and in morphology among different nuclei, across individual nuclei, and there's really an exquisite array of geologic features that we now can resolve on some of these comets, which I would love to talk about, but that's a different talk. And as we sit and look at these at this scale, we can certainly say that we still don't understand what the origins of this diversity is. And in particular, is a constant battle in our field to try to understand what of the things that we're seeing represents diversity in the formation, where and how and when these things put together, and what of it has to do with how these comets evolved as they start warming up and losing their ices. But for certain, they do not look like dirty snowballs or snowy dirt balls, and they don't seem to be in any way simple aggregates of materials. They're quite complex. And we now look at all 6 of the comets that we have images, resolved images of. I've blown them all up so they are different sizes, but you start to see a pattern. And in particular, 5 of these 6 bodies, the exception being Vil 2, are lumpy, right? There's 2 lobes on Borelli, there's 2 lobes on Hartley 2, there appear really to be 2 lobes even on Halley and on Churyumov-Gerasimenko. Vil 2 is the oddball. And even Temple 1, if you look at it, you can start, doesn't take long till you're convinced there might be 3 lumps in Temple 1. And we now sit back and go, well, this suggests that comets probably formed as cometesimals, that is, smaller bodies that accreted independently and then later formed together. And this concept of how comets is formed was really enforced when the New Horizons spacecraft got to Arrokoth, which is 10 times bigger and much farther away, 43 AU, but it too appears to be a contact binary. And in addition, you can see just by staring at these objects, there's some things in common, but a lot very different about not just the shapes, but the surface morphology of these guys. Okay. There are also pretty significant variations in the activity. That is the material that's coming off these comets as they get close to the sun. One of the surprises is that we originally thought that we had water ice on these comets, that it was water ice that was driving the dust, and it's dust that we see as activity, until we started looking and got better and better data and could get out to farther and farther solar distances. And we expect water sublimation to start happening inwards of about 2.5 AU, roughly speaking. And yet we observe now many comets at very large distances, greater than 15, greater than 20 now AU. And here's a couple of examples of comets. This is between 8 and 7 AU. And we had to recognize that the dust that we're seeing can't be driven by water at those distances, but other volatiles, maybe perhaps CO2, CO even, maybe even things, a bunch of other possibilities that exist. There's also a tremendous diversity in how comets behave, how their activity changes with rotation, changes with orbit. Comets have jets that have different shapes. They have trails, they have tails. Some comets actually fragment and break up. We don't really know why. And some comets have sometimes regular, but mostly irregular outbursts where just all of a sudden they have much more activity than they did before. And I just showed you one example, an oldie but a goodie from the deep impact data of Temple 1 when we were on our way to the closest approach in our impact experiment. You can see this is what we call a light curve, change in brightness as a function of time. And it's pretty regular, except for some pretty obvious differences, like right here, all of a sudden it got bright, and another one right here. And one of them, the last one here, is blown up, and you can see that the relative increase in brightness as a function of time, we're now 10 days out from the closest approach. So the comet in and of itself decided to increase its activity. You have a big spike, and then it falls off. We've seen these now, small scale. They're still among the largest, and it's not clear exactly why these kinds of things happen. But there is this, again, much more complexity than you might imagine from an old concept of the snowball just slowly sublimating with time. Another really important example of activity comes from the comet Hale Bopp, which is a very large comet. It's 40 kilometers. It comes from the Oort cloud very far away. Its farthest distance is almost 400 astronomical units. And it's a highly elliptical orbit. So this is its path over here. That's the closest approach. It's not even in the plane of the solar system. It doesn't spend very much time near the sun. It spends almost all its time very far away. And what you're seeing here on what we notionally call the Christmas tree plot from Nicolas Bivet is millimeter wavelengths observations of this comet as a function of distance from the sun. So it's inbound here till it gets its closest approach, and outbound. And what you can see, the top is water, the top is OH, and then CO and a whole bunch of other molecules. And they all behave kind of like we hope. That is, you get more and more activity, more emission of materials as you approach the sun, and as you go away from the sun, they almost beautifully systematically and symmetrically decline. Unfortunately, that is not what most comets do. And a really good counterexample of this is the comet Garradd from 2010 or so. Again, it has a very strange elliptical orbit. It's not in the plane of the solar system. It's coming probably from the Oort cloud. And you can see, first, if you look here with those squares in black and green, this is water. And this is a function of days from perihelion. So you can see it peaks in perihelion. It peaks in output of water way before perihelion. So it's not symmetric around its closest approach to the sun. And that's water. Other things, and this is very unusual case, is the circles down the bottom are CO. And a bunch of measurements from telescopes. This is actually a deep impact spacecraft measurement. And you can see that CO turns on here about 150 days before perihelion and just keeps on increasing right through the closest approach to the sun. So something about the thermal history or the thermal influence of how solar heating is affecting this comet is really fundamentally different, for example, than the previous one we just showed. But if we sort of sit back and kind of look at the surveys of what we know about the composition of comets, it even gets more complicated. So these are two really fine fundamental surveys of the composition of gases, which we've measured from the UV through the millimeter over the years. And the two take-home messages is there's tremendous diversity. On the right, you see a plot in gray is the average abundance relative to water in percent. And the green bar shows you the extent, the range of possibilities, and also the sheer number of molecules that we've been able to identify on comets. So these were all frozen materials that sublimated into the coma. And here from the infrared plot here from Neil De La Rosa is, again, a shot that shows us a bunch of different ratios of different materials. And you can see there's huge variation. And the difference between the red and the green in this case is Jupiter family comets in red, which are short period, are already sitting in the inner solar system, versus Oort cloud comets that are from far away. And you would think that there would be a difference between the two, but there's really no pattern. It's just all over the place. And finally, not knowing that Adam McKay was going to be in the audience, I'm glad I included this one. Our collective favorite really strange comet is R2 Pan-STARRS. It's often called the blue comet because you can see in this beautiful amateur astronomer's image, it is not green as typical of comets. That means it has no CN, no C carbon materials reacting. It's again a very long period comet. It goes out to 740 AU on a 20,000 year orbit. But the interesting thing about this comet is that it has no, it is very rich in CO, it is very rich in nitrogen, but it has almost no dust, and it has almost no water. In fact, the water to CO ratio is less than 0.1, which is really quite impressively low. And I'll show you here that it is very different from almost all of the other comets we've ever seen. So taking all the comets on average, you can see that most comets are in fact dominated by water. They also have a pretty good amount of CO2 and CO in it. But R2 Pan-STARRS, no water. It is dominated by CO and has an unusually high amount of nitrogen, as I said. So what is this particular one telling us? It could be an end member that perhaps formed far enough that it was able to accumulate nitrogen ice in its materials, or it might actually really not be the same as all the other comets, which we think formed basically or created themselves at the size they more or less are. It might actually just be a fragment of a much larger object, a differentiated trans-Neptunian or Kuiper belt object that we're just happen to be seeing a chunk of. The good thing about working at comets is we always get new surprises, and this was one of them. Okay, so let's talk about hyperactivity in comets. Let me say, first of all, there is no formal definition of what that means. I'll come back to that in a second, but also point out it is just another dimension of the complexity of comets we didn't even have a clue about until we started understanding how nucleuses, cometary nuclei, interact with the coma. And it turns out to be that this particular population showed us some things that we weren't obvious in other comets. So as I said, there's no formal definition. What it is not an issue of the comet's focus. There are many, many materials we have seen, particularly at Rosetta, of a complex hydrocarbons, but that does not include iridolim. So it has nothing to do with the generic sense of hyperactivity. What it is, instead, is a recognition from ground-based observations that some comets produce large amounts of water given their size, almost too much water in many cases, given their nucleus size. So one interpretation of that is that they have a very large fraction of their surface is active. But it's hard to understand how you can have nearly 100% of a comet's surface be putting out water. Alternatively, which of course is the answer on some level, is that activity on comets is not simply correlated to the surface area. And one often talks about in cometary science, if you don't know anything about the nucleus, and for sure before we knew anything about nuclei, but even now, our basic model is that they're a spherical cow and that they emit gases everywhere. Well, these hyperactive comets certainly suggest that that's not possible. Their presence strongly suggests that we fundamentally don't understand something about how comets work. And if we could figure out hyperactive comets, we might get some insights into all comets. So the first recognized comet that was termed with hyperactivity, as Rickman and Jorda defined it in 1998, is the comet 46P Wortman. Wortman was studied intensely because it was the original target for the Rosetta mission. Now, you probably know that it didn't end up being the target. There was a really substantial launch delay, and by the time they were able to launch, they had to go to a different comet. But in the around the 2000 or so, there was lots of studies of Wortman because they were expecting to go there. And it was found that Wortman had an active fraction of nearly 100% when it was observed at perihelion. So that means the comet produces more water than can be explained by the sublimation, even if it occurred over the entire nucleus, or nearly so. And I should point out that Wortman is about a kilometer in diameter. It is a small comet. And at the time, there were lots of suggested causes for what could be going on, and they ranged from everything from internal sources, that there was some extra energy source, which is always pushed towards the transition from amorphous to crystalline ice because that produces energy. But there's no real evidence of that. But there was a lot of speculation at the time that maybe there's some extra sublimation of water ice that has nothing to do with the nucleus itself, but material that was expelled from the nucleus. And suggestions ran all the way from grains to large size fragments that may have broken off the nucleus that would be causing this activity. And since the time of Wortman, we have identified a few more hyperactive comets. In particular, there are 3 more small short period comets, which you can see here. This is a plot of effective radius versus active fraction. And there's a whole bunch sitting here with an active fraction of about 1. So these are the 4 sort of standard hyperactive comets. There's another one, 73P, which indeed we know is fragmented. So that is why it has more activity, because it's in pieces and it has more surface area. And then finally, there's an Oort cloud comet from long distance, Hyakutake, which probably falls into the category of it is sublimating nearly most of its surface. But we really don't quite understand this one either. But the ones that I'm really referring to are this cluster of 4 small comets that seem to have nearly all of their surface covered, emitting water. In order to tell this story, I need to talk a little bit about deep impact. I hope most people know that we had a very successful impact experiment at Comet Tempel 1. And afterwards, we found ourselves with a fully functioning spacecraft. We didn't have the impactor anymore, but we did have a very large telescope, a spectrometer, and a couple of other cameras, and a fair amount of fuel left to figure out what to do. The PI of Deep Impact, Mike Ahern, even before we launched, among the targets that we were potentially go to, zeroed in on 103P Hartley 2 because it's one of those 4 hyperactive comets. And in fact, in many ways, it is a twin of Wortman. Another way to look at it is this is a plot of mean radius versus the production of water. And these are the targets that we have visited with spacecraft. They're all sort of, you know, modest on top of each other, same size, same activity. Wharton, where the Rosetta wanted to go, and Hartley 2, where Mike wanted and ultimately did go. And from what we knew about those two targets at the time, we really couldn't really say anything. They were about as close twin comets as we knew. Also, Hartley 2's geometry meant it was much closer to the sun, so we had would have really good signal to noise. However, as politics and budgets would have it, we ultimately proposed a comet that was much easier to get to. It was a shorter path, 85P Botan. I'm guessing nobody's ever heard of that comet, and there's a good reason. We had only seen it twice before, and despite heroic efforts by Karen Meach at the University of Hawaii, we could not find it when we tried to figure out exactly where it was. And that is because comets are, unlike asteroids, they are emitting material and they're kind of carrying their own jetpack. And that jetpack can actually change the orbit and the rotation of comets pretty dramatically over time. So either it moved farther than we thought, or in fact, it broke up and just disintegrated. And of course, we can never know. But we didn't know where it was. And so Mike Ahern and I have what I suspect will always be only the two people who will ever go to NASA headquarters and tell them, sorry, but we've just sent your spacecraft to someplace where there's nothing. That was a difficult conversation. It sounds funny now, but it wasn't so funny then. We did persevere and we got support from headquarters, and we did change our target to Hartley 2, where Mike always wanted to go. It just took us two years longer and therefore was more expensive. It was a very complicated orbit. We had 5 Earth-Moon gravity assists to get there. And one of the exciting things that happened because of that is completely coincidental, unplanned. You may know that the Moon Mineralogy Mapper team, which I was a part of, discovered a hydration feature on the surface of the moon. We were internally very nervous about this because it was the end of our spectrometer, around 3 microns. And I pointed out that a couple of months later, Deep Impact was going to fly by the moon. We had a beautifully working 1 to 5 micron instrument that we were going to turn on the moon anyway. And if there was a water feature on the surface of the moon, we would find it, and we did. And that was very exciting for me personally, and whole nother talk, but there we go. We did eventually arrive at the flyby of November 4th, 2010. And just before I thought I would share this, I haven't dragged this one out for a long time, but this is October 28th. This is our high resolution camera looking at Hartley 2 as we approach, and hopefully this works. You can see, much to our glee, this comet has a whopping jet. We're of course seeing dust in the camera, in the jet from the camera, and as we get closer and closer, we're watching it rotate. Its rotation rate is on the order of 18 hours. And so as we approached this comet, we were getting pretty excited because we've never seen this kind of activity from something that we were about to fly by. I suspect the engineers might have been getting a little nervous, but you know, this was pretty cool. So this was our view going in. This is the day before the closest approach. I also want to pause here literally and point out these little spots here are stars, and those are point sources, and normally they look like point sources. What you're seeing here is not compression, but little circular rings that if you stare at it, I'm sure you can't see on your screen, they're actually triangular. That is the result of the fact that our big telescope was out of focus. That has some negative implications, but it has some positive ones too. And just keep that in mind, that if you're actually observing a point source with this telescope, you will see it circled by the point spread function. So some of the light will spread out and ring itself. That's going to become important in a minute. So this is what Hartley looked like up close, about 10 minutes plus or minus closest approach. Again, there's some really interesting morphologic features that I would love to talk about, but I will not in this talk. What you can see is, and I should say we flew underneath it. So we're seeing from one side to the other, having flown underneath it. You can see this is this big jet that we've been watching that you saw rotating here. It's very unusual to see. In fact, it's never happened that you could see a jet this well and still see the nucleus. What you're seeing here is dust in the jet. You also see this bilobed obvious nucleus here, but also most importantly for this talk, the two lobes of Hartley 2 are connected by a very smooth waist. That's actually the gravitational low of this particular object. One of the things we did was realize that ice is not covering the entire surface of this nucleus. This is a color image, and this is blue slope, which is kind of icy, and the red part is the nucleus. We see ice along the terminator, which we think is a morning frost. So it's not producing so much activity because there's ice everywhere, because there isn't. We don't see any large fragments, but we do get a hint that if you look in this jet, it's blue as well, which suggests that there might be icy grains. And when we looked at the images themselves, we see icy grains in the sky. This should be dark sky. We shouldn't see anything. But what you can see is the individual clumps of ice in the nucleus. They're each ringed in the Coma by the fact that we have this out of focus telescope. I won't let you stare at it too long. We can deconvolve some of those issues. And here you see the icy grains in the sky behind the nucleus. In fact, there's just tons of them everywhere. And there's so many that they're reflecting enough light that we can see the dark side of the nucleus that's not lit by the sun. That's not supposed to happen. There's that much material in this nucleus. We actually were able to trace these, about 50 particles or so, as it approached in our images. And what you're going to see is this is the path of individual grains. And as we move around with the nucleus centered here, you'll see each thing move. It's going to turn yellow. You can't, I'm sure on your screen, see the individual grains, but you can see here, for example, we're tracing this path through here. And what we discovered within about 30, they're not escaping. Most of the grains that we saw were moving at less than ½ meter per second. And that's on the order of 10 to 20% of the escape velocity. There's not a lot of gravity on this guy, but there's enough, evidently, to keep these grains. So if they're going to go up, they're going to come back. And that is telling us that there must be fallback on cometary nuclei, which is not something we'd ever expected. So as we try to piece together Hartley 2, it becomes very complex, and I hope I can walk you through it. The infrared spectrometer results become very important. First of all, this is that jet we've been watching for a long time, and this is a map of CO2. So more is white, and you can see this jet off the little end of the nucleus is in fact dominated by CO2. And in fact, when we measure the comet in its entirety, it has a higher than average abundance of CO2. So we have this CO2 jet off the small end of the nucleus. We looked for water ice from the water ice absorption at 3 micron, and we mapped that. And that's over here. Again, white is more. And you can see there's a huge concentration of water ice here and a little bit down here. But there's a very strong correlation between where we see CO2 and where we see ice. Big surprise for all of us is when we look for water vapor, so not ice, we didn't see the water vapor where the ice was. We kind of see water vapor everywhere, but there's definitely a concentration here emanating out of the waist, this smooth waist between the two areas. So we got a lot of stuff coming out of this little nucleus in different places. But when you think about it, if you have CO2 ice, CO2, it's grabbing, evidently, water ice out of the nucleus. It's dragging it from below. that material will, some of it anyway, is going to fall back down to the nucleus and become the source for the water vapor. So you've got water ice coming out from inside CO2. It's some of it slow enough to be redeposited on the nucleus and actually emit water vapor later itself. And this was the first time I ever uttered the word sedimentary processes on a comet. And the fact that material is moving from this end, inside this end, and ending up over here. This is a very complex system for something that we thought might have been a snowball. So Mike Ahern kind of put all this together, and I'm going to walk you through it to tell you about why this, what does this have to do with hyperactivity. But the concept is that some volatile gas, in this case CO2, is sublimating from the interior. You can see that here. It drags out with it dust and water ice, which are of course less volatile. This material ends up in the coma. Some of it is is moving slow enough to fall back from the gravity of the comet and ends up in this case on the waist. But other grains that can escape the gravity, which doesn't take too much, go out into the coma and they experience something called solar radiation pressure. That is pressure from the solar wind, which pushes them tailward. And these grains, the ones that escape the nucleus, end up collecting in the anti-sunward direction, and they eventually sublimate and provide a secondary source for water. So this answers the question, why are hyperactive comets so productive? The answer is because they have two independent sources of water. The nucleus, like most comets, but also these icy grains in the coma. So there's some evidence from Hartley 2 itself that this is really happening. What you're seeing here is now not ice, but water vapor at much larger scales to try to understand what's going on. So we continuously monitored this comet every couple of hours at least, and looking at the water vapor. This is 2 hours after the encounter, so our field of view is 45 kilometers. 6.5 hours out, we're at 135 kilometers. The comet, the nucleus, is somewhere which we can't see where that crosshair is. More is white here. And one of the things I hope you can see is that at 2.5 hours, there's sort of a symmetric contribution from both the water coming off the nucleus in the sunward side and something in the anti-sunward behind the nucleus here. At 6.5 hours, you can see that it's a really asymmetric distribution, and there's far more water coming from the anti-sunward side. That is, this is the sun direction. So out here in the coma, we're dominating the water species, and there's relatively less coming out of the nucleus. So this change of nuclear source versus the amount of material that is in the coma actually changes with rotation, which is a very fascinating subject that we're still working on. But what's really cool when you have spacecraft data, and in our case, it was planned that we would have ground-based data at the same time, is we can see some of these effects on the ground as well. We can't, it's very difficult to measure ice. We do it sometimes in ground-based telescopes, but we can measure OH, which is comes from water evaporating and eventually dissociating. And now the field of view is 64,000 kilometers, and yet you can still see this is the sun direction. So this enhancement in the anti-sun direction is always there, despite the fact that the comet is rotating underneath. So at this scale, we're still seeing evidence of icy grains sublimating in the coma. And because we have the spacecraft data, we really can understand it. This opens up all sorts of possibilities. And perhaps the most fun one was Wirtanen, the comet we started with that was supposed to be the definition of hyperactive back in 2000 or so. It came very close to us in December 2018, 0.078 astronomical units from the Earth. Wonderful campaign. So it is this twin now of Hartley. And we can see in the ground-based data in the OH, again, this is the sun direction. No matter what's going on with the comet's rotation, we're still seeing this anti-sunward concentration of water, which we now which we now understand is an indication of the icy grains in the nucleus. So the two comets are helping us understand each other, and they're being self-consistent. So finally, I wanted to talk about Fallback, and I'm a little behind schedule, so I'm going to probably skip a couple of things. Rosetta 67P is an interesting comet. One of the reasons is that it is highly seasonal. It's 52-degree obliquity, so it's tilted, and it's very eccentric, like most comets. And so the side that comes closest to the sun is the southern hemisphere. It's not there very long. In the northern hemisphere, by the time it sees the sun, it's much, much farther away. And in fact, the net difference is that there's 4 times more sublimation in the southern hemisphere because it's so close to the sun than it is for the northern hemisphere. And this has pretty huge implications, we found out, on the body, because the northern hemisphere is covered in dust, and the southern hemisphere is almost completely absent of dust. And it is only active near perihelion. And what's actually happening with this comet, and it's quite a shocking dichotomy, the boundary between the northern and southern hemispheres here is quite sharp. What's happening is material from the southern hemisphere, when it gets close to the sun and is heating up, actually gets deposited on the northern hemisphere. And they couldn't be more different. And the other way that we know that they're more different, that they're very different, is the southern hemisphere is really quite icy because all the dust has been removed, whereas the northern hemisphere, which is shown here as a red slope, is very dusty. And what you're seeing here is mass movement of material from one hemisphere to the other. And this is not so surprising. It's not that it only happens in this strange comet of CG, but we see these same kinds of dust deposits now all over lots of comets. And so we're recognizing that moving material, and some of it falling back, is pervasive on comets. So what does this mean for all comets? Well, the same mechanism that drives hyperactivity on comets, hyperactive comets, must be occurring on some degree on all comets. We can see water ice on a steady state on many, many comets of all sizes, and we can infer from water and gas, H2O gas and OH, asymmetries in many comets. So we see this concept of icy grains sort of indirectly in many places. But it's not just water and CO2, as we saw on Hartley 2 that's going on. It could be CO2 ice in a colder CO, or methane. It could be methane ice in CO in some of the more active comets that does the same thing. And it's likely that all comets do produce material that goes into the coma and then subsequently sublimates. It's just that the proportions change. In the case of our hyperactive comets, the proportion of material in the coma that's producing water is something like 40% of what's done in the nucleus, and in many cases it might be a lot less. And the other issue is that grains fall back and they alter, because if they've gone up and they start sublimating and they come back and this cycle could continue, you could do some pretty strange things to the chemistry. And I want to just talk for a moment about fractionation. Comets that have the highest active fractions also have the most Earth-like ratio of heavy water D to H. So here you're seeing active fraction. Again, 1 is 100%, and the amount of D to H. And as you increase the active fraction, you get more and more Earth-like ratios. And this can be explained by hyperactivity, because if you have a larger proportion of material coming from the icy grains that came straight out from the gas, from the depth, that originate from the interior, they're going to be more pristine. And all those materials that are on the surface of the comet that have been altered and maybe deposited and sublimated maybe multiple times are going to be more enhanced in the deuterium, the heavy isotope. So if you have more grains, you're going to be less fractionated. And that brings me to my last real point, which is what are the implications for cryogenic sampling of comets? Our goal, the only reason to do a cryogenic frozen sample, is to get the most pristine ice possible. And we want it to be unfractionated. one of the problems in figuring out how to do this traditionally is assuming that we have to go into the interior of a comet to get these samples. That's hard to do. It's hard to know how far you have to go, and it's really hard to do that without actually altering the sample you're trying to pick up. But the Coma grains themselves have been taken by the cometary gas, put out into the nucleus, essentially unaltered. Because remember, if like in the case of Hartley 2, you have water grains in CO2 gas. They're frozen. The CO2 is 100 Kelvin below water sublimation. So they're being taken for us, pristinely frozen, out of the interior of the nucleus and dumped into the coma. So if you're just trying to get water, for example, going to Hartley 2 and grabbing some of those grains nearby at 1.6 AU would be pretty simple to do. And if you wanted to sample more volatile grains, you would have to find comets that are active at larger AUs, for which we have many. So I'm going to summarize here that Mike's model that he came up with is a mechanism that does occur in all comets. It produces these two sources that can work in volatile pairs, and it establishes that we have a very complex interaction between the nucleus and the coma. And finally, I think importantly, in studying these comets, we really were able to understand for the first time that materials fall back, that you have sedimentary processes, you're moving materials around comets. This thermal alteration does change the fractionation of the surface and is a challenge to cryogenic sample return as typically thought about, and that sampling the grains in the coma may be more prudent. Okay, I'm going to stop. Sorry I went slightly longer than I meant to, and while we're go through some questions, I just wanted to put up for a minute a picture of Mike, for whom much of what you've seen today, I had the privilege of discussing some of these concepts with him while he was still around. Okay, thanks.
Thanks so much, Jessica. That was a really great talk. So we have